Okay, so if you remember back in Chapter 1, we talked about the explicit formula for a sequence, and that's highlighted here in this first sentence. Remember, the explicit formula gives an expression for the nth term of a sequence in terms of n. In other words, if I want to figure out the 30th term in the sequence, the explicit formula is the best way to do that. However, we learned in the previous lesson about a recursive formula. That gives just the first term or first few terms of an expression and tells us how to find the following terms. In other words, a recursive formula, the advantage to that one is it's nice when we want to find the first 5 to 10 terms of a sequence. But if I want to find like the 50th term of the sequence, it's not so nice, because in order to find the 50th term, I would first have to find the first 49 terms to be able to determine what the 50th term would be. So both the explicit and the recursive formula has its advantages and disadvantages. Now, the thing about these is, remember, these are giving us formulas for sequences, and it's important to remember, as I have written in red there, that the domain of any sequence is a set of all positive integers. So the domain is going to be like 1, 2, 3, 4, 5, and so on. There's not going to be negative numbers in our domain, and there's not going to be decimals in our domain. Because today, the reason why that's important is today we're going to be looking at graphs of sequences. And so when we look at the graph of a sequence, since it's just going to be the positive integers, our graphs are all going to be in quadrant 1. So let's look at how we would do that with this first example. So it says to make a table of values for the first 6 terms of the sequence. So I'm going to make a table. You can do it horizontally or vertically. So our x is going to be what we put in for n, or our term. Our answer is going to be our y, or a sub n. So the first term in our sequence we get from right here, it's -2. To find the next term in our sequence, we're going to take the previous term and add 4. So I'm going to find the second term in the sequence, I'm going to take the previous term, which is -2, add 4 to it, and that gives me +2. To find the third term, I'm going to take the previous term, which is 2, and add 4 to it, so it's going to be 6. So we're trying to find the first 6 terms here. So the fourth term would be the previous term 6, plus 4 is 10. So this would be 14, and this would be 18. Now when we go to graph these by hand, it's really important to try to think about our scales. Okay, we're going to have our x-axis, it's okay to count by ones. Okay, so we're going to count by ones here. But the y-axis, we have to go all the way from -2 all the way up to +18. So it's a pretty broad range there. So if you think about it, we have probably the best way to count here would be to count by 2s. You want to make sure that when you pick a scale, you want to pick a scale that's small enough where it'll fit on the graph, but not such a big gap between what we're counting by, where when we graph it, it ends up being a really small area on our graph. We want to be able to have a good picture of what the graph is going to look like here. So we're going to start with -2. Oops. Where x is 1, y is -2. And then we go to where x is 2, y is +2. By the way, when we do this, you want to make sure that you write down at least one of the numbers on the scale. You don't have to list them all out. Sometimes list them all out makes it a little easier when you go to graph it, so you're not having to count each time. But you need to identify what you're counting by. So I'm counting by if you change it to something other than 1. Like the x-axis, I'm not going to write down. If you want to, you can write down that you're counting by 1s, or you can just leave it, and I'll assume if you leave it that you're counting by 1s. But make sure that if you change the scale, to put down at least one of the numbers on there so I know what your scale is. Okay, so at the 0.22, the 0.36, so 2, 4, 6 would be here. The 0.4, where x is 4, y is 10, 2, 4, 6, 8, 10. And the 0.514, so 2, 4, 6, 8, 10, 12, 14, and 6, 18. Now I know we're in the habit, ever since preschool, we're taught to connect the dots, but we are not going to connect the dots here. Again, the reason why is because of what we set up here. The domain is going to be just a set of all positive integers. There are no decimals in here. So if I were to connect these with a line, that would be wrong, because connecting them with a line, really there is no such thing as a line. A line is essentially an infinite set of points. So by connecting these with a line, it's saying that you're including all the points in between them, which we don't want to do. So we would leave it just like that. Okay. Now this one puts it in terms of words. We don't have the recursive formula here. They just give it to us in words. But I want you to try this one on your own. You're going to add 22 stones to a pile every night. How many stones are in the pile after the nth night? So after the first night, just to give you a hint, you would start out with 22 stones. So go ahead and find the first 6 terms of the sequence and then graph it. And then so pause the video and then hit play when you're ready to check your answer. Okay, so let's go ahead and check your answers here. Again, if you had used X and Y here, that's no big deal. I wouldn't mark that wrong. The only reason why we do that is because we're putting this in terms of a sequence where n represents the term number, a sub n represents the value of that term number. So we want to find the first 6 terms. So the first term represents how many stones there'd be in the pile after the first night, which would be 22. And every night you're going to be adding 22 more stones to the pile, so you'd be up to 44, 66, 88, 110, and 132. So now this one, your scale, you got to go from basically 0 all the way up to 132. So a good scale to count by here might be to count by 20s. You don't, by the way, never pick a scale that's your actual numbers. So don't say it's going to be 22, 44, 66, 88. Don't do that. Okay, even if you're increasing by the same amount, it's a bad habit to get into. And plus, it just looks weird. So we're just going to always pick a nice number to count by: 5s, 10s, 20s. So this one we're going to count by 20. So we put 20 here. Count on the x-axis, we'll count by 1. So the point 122, a little bit above 20 there. Point 2, 44, so 20, 40. 40 would be right here. And then 66. 66 would be right about there. So we're getting higher and higher above the line each time. 88 would be almost halfway, because 70 would be halfway here. 5 and 110. So here would be 100, so 110 would be halfway. And 6 and 132. So this would be 120, 130, so this would be a little bit above halfway. So we just have to graph the first 6 terms. Again, do not connect them with the line. If you connect them with the line when you're graphing with the sequence, and if it was a quiz, I'm going to take off points. So don't connect them with the line. You might want to make that note in your notes there. Okay, so we looked at recursive formulas. Now we're going to look at graphing an explicit formula. So here they ask us to graph the first 6 terms of the sequence. So what we're going to do is, with the space that they gave us, I'm going to do this horizontally. Okay, so now when we're given an explicit formula, just to review, we're going to put 1 in here for n to find the first term. So we take 41 times the first term, 41 times 1, and then add 72 to it. Well, 41 times 1 is 41. Add 72, you get 113. Put 2 in here. 41 times 2 would be 82, plus 72 would be 154. 41 times 3 would be 123. Add 72, you get 195. The next term would be 236, 277, and 318. Okay, so now when we go to graph this, one of the first things we need to do is figure out what scale we want to use. Again, on the x-axis, we can just count by 1s there, so we'll go 1 through 6. But on the y-axis, we have to go all the way up to 300. So what I'm going to do is, it looks like maybe counting by 50s would be a good scale to use. And what you can do too is, if you don't want to start and count every single one, I am going to still count by 50s, but I'm going to include only every 100. So we'd have 200, 300, to 400 there. Okay, so now the point when x is 1, y is 113. So here's 100. 113 would be a little bit above there. 2 and 154. Well, 150 would be here, so 154, a little bit above 150. 3 and 195, which is just shy of 200. 4 and 236 would be about there. And 5 and 277, well, 275 would be halfway, so it's a little over halfway. And 6 and 318 would be just shy of being halfway. So again, there's our sequence. When we go to graph the sequence, we don't connect it with a line. Now part B says to graph the function. The difference here is when we graph the function, it's going to have the same set of points, except for when we graph a function, we do connect it with a line. So the function, we use a line. So as far as describing how these would be different with a explicit formula, or with a sequence, these are always going to be discrete. Remember, discrete means that you don't connect them with a line. Functions, on the other hand, are continuous, meaning that we do connect them with a line. So that's the difference between the graph of the sequence and the graph of a function. Well, we're going to end by looking at this story problem, dealing with this plant. It's called the sneeze wart plant, and surprisingly enough, this is a real plant. It's not something taken out of Harry Potter. It is a real plant, and what it does is it starts out when it's growing as a single stem. After 2 months of growth, the stem sends off a shoot that becomes a new stem and produces a new shoot every month thereafter. The new shoots must mature for 2 months before they are strong enough to produce shoots of their own. Let f sub n be the number of stems in month n. The first 2 terms are equal to 1. Beginning with the third term, each term is found by adding the previous 2 terms. Now, it's pretty cool because math is found all over in nature, and this is just one example. This is where nature follows what's called the Fibonacci sequence. We're going to talk about that here in a minute. But the Fibonacci sequence follows this pattern, where the first 2 terms are equal to 1. So to write a recursive formula, the first term would be 1, and the second term would also be 1. Now to find the second term, each term is, not to find the second term, but to find the next term, each term is found by adding the previous 2 terms. Well, in our previous lesson with recursive formulas, we talked about the fact that we use sub n minus 1 to refer to the previous term. Well, if I want to refer to the term previous to that one, we would say sub n minus 2. So this means we're going to take the previous term plus the one before it. Now the key here is that you would use this formula for the third term on, or starting with the third term. That's what that piece represents. Because we already know the first term and the second term are both going to be 1. Okay, so now we want to find out what the first 10 terms are going to be. I guess this would be f sub n. Okay, we already know what the first term is. The first term is going to be 1, and the second term is going to be 1. So this is telling me that to find the next term in the sequence, you add the 2 previous terms together. So 1 plus 1 would be 2. So to find the fourth term, I would add the 2 previous ones, just the 2 previous ones. 1 plus 2 is 3. So to find the fifth term, we add the 2 previous terms. 2 plus 3 is 5. 5 plus 3 is 8. 8 plus 5 is 13. 13 plus 8 is 21. 21 plus 13 is 34. And 34 plus 21 is 55. Now when we go to graph this, it's going to look slightly different from our other graphs. But again, our first step is always the same. Figure out what our scale is going to be. So our x-axis, again, we have enough space here to count by 1s. On the y-axis, let's count by 5s. So we'll run off a little bit, but that'll be okay. So when x is 1, y is 1. Well, if we're counting by 5s, That makes that just on top of the line there. For the first two terms, the third term is going to be 2. The fourth term will be 3. The fifth term will be 5, so that's easy to graph. The sixth term is 8. The seventh term would be 13. So here's 10. 13 would be a little over halfway. 8 would be 21. 9 would be 34. And the 10th term of the sequence would be 55, which would be right up there. Again, this is a sequence that we're graphing, so do not connect the points with a line. So basically what we just talked about is that's a representation of a Fibonacci sequence. Just a little background information. You don't have to get this in your notes. You won't be tested on this, but I think it's important to know where some of the math is that we're talking about, where it comes from. And so a 12th century mathematician by the name of Leonardo of Pisa, he wrote under the name of Fibonacci, and he came up with this sequence. And this sequence, like I said earlier, is found all over in nature. In fact, there's a publication called the Fibonacci Quarterly. Maybe you've heard of it. Probably not. That's devoted to the mathematics that we get from the Fibonacci, or where we could find the Fibonacci sequence used around us. So again, this is about how to, this lesson was all about how to graph a sequence. The key for this lesson can be summed up right here. When we graph a sequence, don't connect the points. So good luck on your assignment.